So yeah, today we're going to talk about high-performance power module designs in power distribution networks. So the topic we're covering mostly is about immediate bus converters and also partially maybe a little bit of point of load. But overall, it's about power modules, which are just conversion points in a larger power distribution network segment. So this presentation here at the very beginning, I will just introduce as a classical application example, a 48-volt rack power distribution network and its conversion points specifically for telecom systems, but that usually is really just the example, and it should translate nicely also in other power distribution networks for industrial applications and so on. So the converters we're looking at today are 16-brick converters. So we have designed two almost identical power supply modules together with EPC, so efficient power conversion, using their GaN FETs. So the first one is called EPC 9143, which is a unidirectional power module, and then its brother is then the 9151, which is almost an identical design. It's just using a different switch node device, and then it also supports bidirectional control. So this tailors in two different application segments, but overall the control schemes, the software, and all the software features are almost identical. So after having a short view at the hardware, we then dive into the control system, and the majority of this presentation is about integrating something we call a Type 4 adaptive voltage mode control with PWM steering and high-speed current balancing. And I think this might cover most of the features that actually push this product forward, helping to solve a lot of problems on application side. So it's less about just building a sophisticated controller for the purpose of just doing it. It actually has a purpose in real world, and we will have a look at what the implications are on a final power distribution network design. Good. So our classical IBC architectures look mostly like this. So you have a 48-volt rail or a 24-volt rail, and there's some AC/DC that provides the rail voltage, and then it's distributed across a wider system. And then at the conversion point where you need lower voltages, this is where they then usually find the so-called intermediate bus converters that have a typical output voltage range of usually something 9 to 15 volts. And then it goes further down to the point of loads, which are then either directly the voltage regulator module for a high-speed load or other conversion points for some whatever load. Voltage levels here on the point of load are usually between 1 and 5 volts. So we have this multiple conversion points, and obviously when a load has a high load demand and starts to create a load profile, then the point of load is the first point that needs to correct the voltage. But there's always a reflection of that load profile, which also gets on the bus. And then this DC to DC converter here on top basically has to deal with the load profiles or damped load profiles of all the point of loads which are connected to its output. And then eventually that chain goes back to the 48-volt rail. So whatever is providing this 48-volt rail is also required to deal with the entire load profile of the complete system. So the larger the system gets, the more challenging these load profiles can become. And decoupling of each of the conversion points is getting highly important, and is one of the major aspects when you design a power distribution network like this, so that every load, basically every noise source in the system is contained in its own network segment, and that its load profile or its noise is generated is not migrating through the system and affecting all the other bus converters as well. So one of the major drivers for more advanced high-speed, high-performance IBCs currently is our 5G systems. So 5G has a significantly higher power demand versus the most recent 4G or LTE network systems. So especially in base stations, so if you compare the power consumption of a base station in 5G, that's almost 4x the power conversion demand of a 4G counterpart. So it means we need a lot of more power to provide to various loads. So a lot of CPU and FPGA systems are integrated that take care about the signal decoding, encryption, and whatever. So the higher demand in power and the more the systems we need is does not necessarily mean that we have more space. So these systems are usually getting more and more cramped, increasing significantly the demand for higher power density power converter designs. So addressing this particular application space, we designed these two 16th brick converter modules using gallium nitride devices with the main purpose of just squeezing the size of the power supply and try to increase the power density as far as we can. So the two modules which are currently available can be tested on this test fixture we see here on the upper right. So here in the middle you see the 16 brick design. It's an interleaved non-isolated buck converter, which is programmable. So you can program different output voltages by default in a range between 5 and 15 volts. Dropping below 5 volt doesn't really make sense because then you're ending up with approximately 10% duty cycle, which means that the dynamic bandwidth you have available is maybe not good enough to really sufficiently supply any kind of point of load. The maximum output current of this modules is 25 amps, so 12.5 amps per phase. And looking at the complete volume of this module with all its components, this gives us power density of up to 750 watts per square inch. So it depends a little bit on the output voltage because the really limiting factor is the current. So we cannot go beyond the 25 amps. So therefore, the power density here is specified between 650 and 750 watts per square inch. When we compare that module against, let's say, a common off-the-shelf 16th brick design, low cost, open PCB, no housing, then we see that, let's say, state-of-the-art is roughly somewhere between 450 and 500 watts per square inch. So by using gallium nitride switches, so the first advantage we get is the smaller size. The second one is that we can operate them at higher switching frequencies without exceeding switching losses. So the wide bandgap devices allow us to turn them on and off really quickly. There's basically no or very little parasitic capacitance. And what is most beneficial is there is no body diet. So reverse recovery is basically non-existent. That means we can turn on and off these switches with an incredibly speed in both directions. And this helps us to squeeze the size of the switch nodes significantly versus a conventional silicon MOSFET design. So using these capabilities, we're now able to get two phases into the same form factor than just a single phase, which further helps us to reduce the current ripple. The current ripple then translates into a smaller input and output capacitors, smaller filters. So that is altogether then helps us to squeeze the size of the conversion point to the bare minimum, which is currently possible, I think, from a point of technology. So when we look at the two derivatives we have created, so the major difference between them is that the 9143 uses two discrete gallium nitride switches and an external gallium FET driver, which in itself occupies a little bit more space. When we compare this then to the 9151, we see that we're using EPC's latest devices with integrated drivers. So that has a couple of advantages. So first, it's a full half-bridge with a half-bridge driver, which is integrated. The only external component is the bootstrap capacitor. So the first advantage is that we can operate the switches at their natural maximum speed. So all the parasitics which come into play here on the left in the discrete design, so components, then parasitic inductance of packages of resistors, gate drive resistors, all of this usually requires us to slow down the gate so that we are never really achieving the maximum switching speed that could be achieved by operating that switch. So we always stay slightly below that. So now as everything is integrated, we can really go push the envelope to the limit, operate the switches as fast as possible. The downside here is that because of the technology and the packaging, or let's say the chip design, is that the integrated devices have a slightly higher RDS on. So when we compare the complete efficiency between the two almost identical designs, then we see that the discrete design is overall still roughly 1% more efficient than the integrated one. However, having an integrated device leaves us more board space. So board space means we can put more input capacitance in there, and then eventually we could even squeeze the size of the board a little bit further. So as we're staying in classical form factors like 16th brick, there's very little point. If you cannot really make a huge difference, then we just use this space to get rid of the heat and to spread the heat over the not very big board space that is available anyways. So when we look at the efficiency a little bit closer, then obviously the efficiency also relies a lot on the conversion step from 48 volt down to 12, 9, or 5 volt. So we see the comparison here on the left. So the lower the step down is, the higher the efficiency. So the maximum efficiency here that's specified here in this presentation is always referring to the 12 volt line. So if you're converting down to 9 volts, then we already lose roughly 1% in efficiency. And if we step further down to 5 volts, then we lose another 2%. So the difference between 12 and 5 volt is roughly 3% in efficiency. Then also airflow has a significant impact. So when we are driving an airflow across the board with 1700 LFM, this is quite a lot, then we can push the envelope a little bit further up. So in the 9143 design, we're getting close to 97% in efficiency. If we refer to, let's say, a conventional airflow, which might be implemented in one of the telecom racks, this is usually in the ballpark number between 400 and 800 LFM. So here at the lower end at 400 LFM, we lose a little bit of efficiency. So this is roughly 0.3 of a percent. So the bidirectional converter is more targeting automotive and aerospace applications, where you usually don't push the envelope to the absolute maximum so hard, while in telecom, it's really all about the performance of the connected loads. So this is where the efficiency is more important, and there is no bidirectional power flow. So this is where the unidirectional 16th brick design is focused on. Okay, so as I said, both designs are interleaved non-isolated buck converters. So a pretty easy, slim, straightforward, low-cost design. So usually when you have a multi-phase converter, the normal control approach is to use an average current mode controller. So the average current mode control is comprised of two inner current loops. Each of the current loops is independently just looking at the inductor current of its phase, and both current loops are supplied with the same reference, which comes from the outer voltage loop. So this ensures proper current balancing without actually enforcing some PWM schemes. So every loop is making sure that the current is correct and in the same ballpark number than its counterpart. So when we look at a system like this and we are trying to implement this in the digital controller, then this can become quite challenging because we need to run multiple control loops in software using the DSP. So the CPU load is increasing with every single loop we are implementing. And considering the high switching and control frequency we are targeting with these IBCs, it's still possible, but it's already eating a lot of the CPU load. For simplifying that system, or let's say to also address more phases than maybe just two, maybe you have a higher number of phases, that would not really scale well. So at some point you might be required to reduce your control frequency and control every other cycle, for example, and then your bandwidth drops, and then the capabilities of meeting the design specs is then at stake at some point when you're just failing to provide enough performance to run the complete control system in real time. So that is one limitation. So when we set up a control system like this, then our final output, so our frequency domain might look like this. The other thing is when you have an average current mode controller, the inner current loop is seeing two perturbations. One is coming from the feedback. So it sees a load step it needs to respond to, but also there's no constant frequency reference input. So the voltage reference will also continuously tweak and change the reference. So when you have a control system which is perturbated by two directions, then obviously this figuring out where your safe operating point and the stability is requires to look at both sides, at the input side on the reference and on the feedback side. So when you're trying to stabilize an inner current loop, there's a maximum perturbation frequency on the reference you need to consider. So every time the reference is changing, the current loop needs enough time to follow. If you're just perturbating too fast, then the current loop might not be able to keep proper track of the demanded reference, and might start to see artifacts like alias frequencies. So it might start to oscillate and interact with the voltage loop. And there's also always the risk of, because voltage loop and current loop will see load steps at the same time. So you will see a large step on the feedback signal, and at the same time you would see the response from the voltage loop also manifesting itself as a larger step on the reference. So there's definitely one frequency at some point where the system will get unstable. Even if each of the loops, when you measure them individually, might still meet all the stability criteria, the whole control system also needs to meet the stability criteria on its own, which is then mainly just focusing on the perturbation frequency of the reference. So when we are setting up a control system like this, that means that we need to start with the current loops. The current loops are then adjusted at decent speed, let's say 10 kilohertz for the sake of an example, at a specific stability, and then you have the voltage loop that perturbates its reference. This perturbation frequency needs to be significantly below the crossover frequency of the current loop to ensure that we're not injecting accidental oscillations. So in this particular systems of these two 16 brick designs, that maximum perturbation frequency of the voltage loop or the current reference is at around 3.5 kilohertz. So when you then put the entire system together and you make an analysis of what its crossover frequency and its response time can be, then this is the physical limit of the control system. And when we are now looking at the planned transfer function of this multi-phase converter, there are more challenges. So here you see a planned measurement of both phases being operated 180 degrees out of phase. So what you would expect to find in a non-isolated buck converter is that you have one resonant frequency at its LC resonant frequency. But in a multi-phase converter, and that which is operated 180 degrees out of phase, you will find a second resonant bump. And that second resonant bump is at twice the resonant frequency. So this is when both converters, so this ping pong between both converters, may result in charges which are flowing between both phases. And that then manifests itself as yet another pole that shows up at twice the resonant frequency. And this pole is visible in pretty much in every control mode. The only way to properly eliminate this would be either hysteretic mode, or a peak current mode. So when we look at this, here on the left, you see a plot of multiple transfer functions across input voltage to see the variations and when and how this second resonant bump develops. And then based on that knowledge, we start to set up our control system to design for appropriate design margins and safety margins. But as you can see here in the average current loop, even if we are able to damp the second resonance, we cannot really eliminate it completely. So it is still visible and still haunting us. If it would be a single phase converter, the gain would just drop steadily and then would give us a better gain margin here at higher frequencies. But with this second bump, unfortunately, we get this flat gain region, which is, if we are trying to push the gain too much, this flat region will come closer and closer to 0 dB. And this is then opening a high frequency noise gate into the control system, and the control system will start to reproduce this. We'll see the effects on this later, also on the design. So this multi-phase resonance is then needs to be dealt with. Means a classical type 2 controller, which would usually be the choice for an inner current loop, this is not good enough because we don't have any poles and zeros left to deal with this high frequency pole. So the different control approach we have been taking with these controllers is now not to go for current loop, but still use a voltage loop approach. But obviously, normal classical voltage loop might not be sufficient. So what we do here is we use a voltage mode controller with of a higher order that gives us additional poles and zeros. So in this particular case, it's a type 4 controller, and we use this additional pair of pole and zero to compensate this additional pole, which shows up here at the higher frequency. So in comparison to the voltage loop, we can now address this point and damp its resonance frequency further down, flattening out this gain region here at roughly 20 kilohertz. And now we have in this region a fairly nice slope of the gain, which also allows us to push the gain up so that we can achieve a higher bandwidth of the control system. So using this technique allows us to go now up from 3.5 kilohertz to roughly 20 kilohertz. And this means that the converter will have a faster step response. So the voltage drop and overshoot at every load step will be minimized. In return, that also means that we need less energy storage. So we need smaller capacitance at the output, and we can reduce the size of the decoupling capacitor. So here is an amplified version of this type 4 controller. And here we have a couple of things. So first, the additional zero we bring in here in the high frequency range allows us to create a new phase boost region. So we are just pumping up the phase in a high frequency range so that we can, when we start to push the crossover frequency, that we still have enough phase margin. So this limit here is roughly at 25 kilohertz. So this is where we will underrun the 60 degrees of phase margin target. The second thing is that now we have a second order system. So the crossover frequency is not necessarily connected to our integrator gain. So we have the capability to adjust the pole at the origin, and by repositioning one of the zeros, we can then increase or decrease the integrator gain while keeping the crossover frequency constant. So we are using this two-sided tuning concept now to balance out the step response. So how fast can we recharge the output capacitor to minimize its size? And the second thing is then whatever output impedance is required to meet of this decoupling cap can now be adjusted by adjusting the integrator gain. So here, if I simplify this bullet plot, by repositioning pole at the origin, the whole gain curve is translated up or down. By repositioning this first zero, we can either increase the crossover frequency, so I can pull this in. So the gain will shell out earlier, will start to drop from a higher level and then cross at a later point, increasing the total bandwidth with a decent positive gain offset. The same is true when I increase the pole at origin frequency, then I can push the zero out and then lower the gain level here in this region, again, coming up with exactly the desired crossover frequency. So once we have found a setup that is working for us, now we use an additional technique called adaptive gain control. And I think this has been introduced on this Power Symposium already a couple of times, so I keep it short here. What this does is it's a very specific kind of feed-forward control, which always tunes the gain to a desired nominal level. So I would analyze and adjust the loop in this case for nominal operating conditions. Let's say 48 volt in, 12 volt out. So once everything is adjusted, I determine this to be my ideal tuning point, and then the software adaptation running inside the cycle-by-cycle control loop will increase and decrease the gain, always keeping it at exactly the same desired level, so that we always come up with exactly the same crossover frequency, the same phase margin, and the frequency response will not change. It's then independent from changes at input and output voltage and also across load. Good. So this second resonant bump, if we are trying to push the crossover frequency to its maximum, there's still a physical limit we have to consider. So when the crossover frequency matches this resonant point, you will see that we might have damped it, but it's not gone. So if the crossover frequency matches this resonant point or even slips into a positive range, then we will see that this resonance that creates this bump is starting to show up in our control system. So the system starts to resonate in itself, and this then manifests itself as a frequency jitter, which becomes visible on the duty cycle. So here you see this falling edge starts to vary a lot, and the jitter is getting worse and worse and worse the more we try to push the crossover frequency up. So this means for these both two systems, 20 kilohertz is pretty much the limit, and this is where we nailed it. So the second thing is when we are pushing up the frequency and we're introducing a zero here to give us another phase boost, we need another pole to suppress high frequency noise at a higher frequency range to end up with decent gain margin. So the closer the two are moved together, the less their effect will be in the system. So we need to keep them apart quite a bit. In this particular case, we place the zero at roughly 30 kilohertz. So it starts to rise one decade early, but okay, there are resonances, so it's a little bit weak, but it's already bringing up the phase in this high frequency range. And then we use the third pole. We now get positioning it roughly 200 kilohertz to add another high frequency rejection point there. So once we have set up this control system, we can now compare the step response to our findings in the frequency domain and see if it matches. So we have adjusted it roughly at close to 20 kilohertz, and this is exactly the frequency we find when we analyze the step response here. So it's also approximately at 20 kilohertz. So this matches. So we have no influence, even not of that flat gain region below the resonance. So we've heard it before. If you have a region that shadows out close to 0 dB, then the step response frequency you might find might be affected by that lower frequency flat region. But in this particular case, the gain is still high enough so that it doesn't influence our step response. So the step response we see here is truly the 20 kilohertz we have adjusted here as a crossover frequency. The slight mismatch between the 19 kilohertz and the 22 kilohertz here is mainly due, also this oscillation is due to this limited slew rate of our load. So the load rises not fast enough to really benchmark the total speed of the loop. Okay, so when we have voltage mode and instead of current mode, this has significant influence on the output impedance of the converter. And as I mentioned, our target should be that we try to minimize the output capacitor. So what's wrong with voltage mode control? By the way, I've stolen these two charts from Steve Sandler, so should he already be on the call, I apologize, but they're really cool, and so I had to steal them. Good. So what's bad about voltage mode? Voltage mode, a voltage loop is highly affected by changes in input and output voltage ratios. So when the voltage across the inductor drops, then we lose gain. So the whole frequency domain we have adjusted comes down. And when we go to a high line condition, then the total loop gain goes up. So it's very, very hard to estimate what the real bandwidth and also the output impedance might be. So when we look at the output impedance, what happens there is that in the lower frequency range, so the higher the gain, the lower the output impedance. And so we have this huge variations, which might then have a better influence on how power is then transferred through the energy storage onto the next network segment. So the great advantage of having a current mode system here is that it's really super tight because it never really changes. It's a first order system, which is quite stable. So if you're going from high line to low line, you might see some variations of the crossover frequency, but it's very stable. The downside, however, about current mode is that because it's a first order system, the level of output impedance you get is what it is. So you would have to readjust the complete control loop gain, and then it depends what kind of device you're using. So if this is an integrated device, that's it. So the only way in matching the output impedance to the capacity is actually reworking the capacitors. So you need to change and select the right hardware component. So adaptive gain control and this two-order system now allows us to first take a voltage loop and bundle all this huge variations in output impedance, bring it to a single straight line, just like in current mode, while the zero-pole tuning that is now decoupled from the crossover frequency allows us to adjust the impedance level. So now we can take a specific portion of the output impedance tuning and do it in software rather than exchanging capacitors. So, and then we can use test adapters, measure capacitance, can see that we can, what the output impedance is we need to meet. And then I take my control system and run a complete measurement with the right capacitor integrated. So in this case, on our text fixture, and I make an unpowered measurement and then a powered measurement. So as you can see in the unpowered measurement, what we are trying to get rid of is this capacitive range. So this should become flat, not undershooting too much. So it should basically match this impedance level here. So when we turn on the power supply, then we can tune the pole at the origin to give us a range here that is running towards this ESR in a pretty flat way. So the tuning of the pole at the origin shows more effect with lower frequencies. So as we go up and we come closer and closer to the ESR frequency of the output capacitor, so the effects are minimized. So it means we have basically just an adjustment of that output impedance level, and we need to push it up or pull it down a little bit to balance out this impedance mismatch. And because here this measurement was so noisy, I think I put a curtain over it and promise to do better next time. Okay, so the tuning goal now is to have an impedance which kind of looks like this. So it should run fairly flat and nice into maybe at or slightly above that ESR point we have measured at the output capacitor. So if we have a system like this, then we are able to have a smooth power flow from our conversion point into the next network segment. And we have basically eliminated every chance of overdriving the system so that our power supply starts to resonate with load steps that might occur in the system, and then the decoupling is optimized. Good. So the controller system we are using here looks like this. So this is just basically a block diagram of the software library we're using. So we have a core piece which performs a classical type 1, 2, 3, 4, 5, 6 compensator. And then we have some extensions, some feature extensions, where we can feed more data in and select specific features we would like to use, like ADC and PWM trigger placement and so forth. In this particular example, we are using the source to feed in the output voltage and then also the input voltage. Then on the other side of the black box, we get 2 duty cycles out. So these 2 duty cycles are identical. We are basically mirroring the controller output onto both PWM modules, producing exactly the same switching waveform, but 180 degrees shifted apart. Then here we have another gain trigger. So that means when the computation inside our filter reaches a point where we need to incorporate the tuning factor, we are calling an external function which performs the adaptive gain observer code, determines the next tuning factor, and that tuning factor is then fed back into our computation loop, and then we are producing this the next control output. Good. Okay, so when we build up the system, we start from a simple voltage loop. So inside the power plant, we have our PWM, and the PWM triggers the ADC to make sure that we are measuring at the right time. In addition, we now sample a second data point, also triggered by the PWM at the right time, which gives us the sample of the most recent input voltage. And as we have just seen, these 2 values are then just fed in the adaptive gain control. So we analyze the voltage ratio across the inductor, calculate the drop or increase in gain, and then we compensate for that by just repositioning the polar 0 inside our digital nonlinear controller. So now as we have 2 phases, we are mirroring this output onto the second phase to have twice exactly the same switching frequency waveform. And this is done by a new block, which we call PWM duty cycle distribution. So this distribution block now gets 1 offset value, which is only applied to the second phase. And this is how we tie in the current balancing, because we still have to consider that we have component tolerances, temperature tolerances. So the currents will never really be properly balanced by itself. There are board parasitics, all kind of influences which might drive the 2 currents apart. And even if we have this hard PWM steering, so that basically just one loop is or one phase is properly controlled, and then all the other phases are just power multipliers, we still need to balance out the currents to make sure that the component stress is distributed equally across each of the phases. So what we do there is we have current sense implemented, although we don't use it directly for the control in terms of an inner current loop. We still sample the current, and we compare the 2 current samples, and the difference between them indicates if we should increase or decrease the duty cycle in the second phase versus the first phase. So this current balancing scheme looks like this. So we have this 180 degree phase shifted PWM waveforms, so PWM 1 and 2. PWM1 is the one that creates all the ADC triggers to make sure that we are measuring current and voltages at the right time. By measuring at exactly half of the signal waveform of our high-speed 500 kilohertz current feedback, so that is not really a triangular waveform anymore. We are using shunt amplifiers, so that means the maximum bandwidth of this device is also just 500 kilohertz. So the current feedback we get back is more like a sinusoidal. It's not really a proper representation of the inductor current. However, the midpoint, so the average current, is still highly accurate, even if the extremes are not. And the second consideration we have to make is that the signal is phase shifted because we are approaching the bandwidth of our current feedback signal. So in digital, it's quite easy. As long as we know what the phase delay is, we can reposition the ADC trigger accordingly in compensating the drift in phase of each of the current feedback signals. Okay, so when we are tracking that current, then we know pretty much exactly what the average current is, even if we have, let's say, an insufficient current sensing circuit like this. So the difference of both currents gives us a result, and the result is a number. So a digital number has always a sign bit as its most significant bit. So what our current balancing algorithm does at the moment is it's just taking the sign bit. And if the sign bit is set, then this is ORed with just the number 1. So this number 1 is the size of the duty cycle adaptation we can do in one single balancing step. So here it is just 1. So we are incrementing or decrementing the duty cycle in 250 picosecond steps. And then we have a range limiter. So should anything go wrong with the current feedback signals, that we don't drop the duty cycle completely or crank it up to 100%, so that it's just staying within an allowed current balancing range. So with every current balancing step, we are incrementing or decrementing this duty cycle offset in the second phase. So it means it never reaches a stable point. It will always go above, below, above, below. So it's something like a very, very simple bang control of the duty cycle offset. But as the step is so small and just is 250 picoseconds versus the complete on time of the converter, that influence is very, very, very small, and it doesn't show up anywhere. It doesn't create noise. Okay, so that basically concludes that implementation of this control system. So as a short summary, so this transformation of this classical control system allows us to decouple impedance control versus bandwidth control, both together. So the high bandwidth allows us to minimize the amount of energy storage we need to decouple the next bus segment. And then the impedance tuning makes sure that our control system behaves well and feeds the power in just the right way into this decoupling cap to properly supply the downstream network segment. So by having this tuning capability inside software that reduces, let's say, the amount of work and efforts you have to spend in component selection, and also if you are integrating off-the-shelf module in an existing system, it requires significantly less hardware rework. So you can take the benefits of having a programmable, adjustable system and tune the system after you have integrated into the system while designing the system around the power converter. That is the major key here.